So we have a few correction from the prior video. One of the correction is that the variance of t is the expectation of t minus expected value of t square. Expected value of t is nothing but the mean values of t, and this, since when we say expectations mean that you have to get the mean values of all of them across all possible samples. So that is why you would do summation ti minus expected value of t square times pi. That would be variance of t. Again, how do we get expected value of t? Expected value of t has the same formula here, which is this, which is the expected value of t formula. But then when we want to do, which is basically just the mean values of it, and then when we want to get the variance is, then you get the expected value of t minus the expected value of t, which is the mean value here for all these values, square it, and then uh, do the probability distribution. That is how you get the variance of t. But when we want the mean square error, instead of doing that, we are doing, and then you take the standard deviation of the estimator. That is the standard error of the estimator. So again, it is the expected value of t minus expected value of t, and then you square it, the square of this expectation. So when you do this, it is nothing but all the values ti minus expected value of t square times pi, where expected value of t is just ti, is just a summation of ti pi. That gives you the expected value of t, and then there is ti here anyway. So that is the variance. But when we want to calculate the mean square error, which is becomes the same thing, but instead of the expected value of t, we use the population theta here. So ti minus theta into pi. So mean square error, we solve this here, and this is the variance of t is expected value of t minus m. M is nothing but the expected value of t, and the MSE is expectation of t minus theta square. Again, when you want to simplify this, how do we do this? That is nothing but this thing here, summation, um, and this simplifies to, so this is quantity. Okay, so moving on, now we're going to do the sampling distribution and its normal approximation. So what it is, the estimator t is a function of the sample observations, and so given the sample data, the value of t, the estimate, because t is just coming from the samples, so we can calculate the value of t. So we're talking about sampling distribution and normal approximation. Now we can calculate t from a large number of samples from a population, so we can get its probability distribution. And so we can take a lot of samples, sample t1, t2, t3, t4, and all and we can get their probability distribution pi, p1, p2, p3, p4. So that is called the sampling distribution of the estimator, and then we can calculate this sort of thing, where this is the PIs, and this is the T1, T2, T3, T4. So this is the sampling distribution, and it can be shown that irrespective of the population distribution, if n is large, then the sampling distribution is approximately normal. So this is the normal approximation of the sampling distribution, that we took a bunch of TIs, each with the probabilities of PIs, then irrespective of how the sample is distributed, this thing is going to be normally distributed, and this is just a central limit theorem. Suppose we use a probability sampling scheme which gives us an estimate. So now we're going to talk about estimate. So if there theta is the population variable and we are estimating it, that will be theta hat of a parameter. So absolute error of the estimator is going to be theta hat minus theta. How do we judge whether how good the estimator is? So we can use normal approximation, and if theta hat follows a normal distribution, theta hat will follow a normal distribution with a mean of theta and a standard deviation of theta or sigma, which is the standard error of the estimator. Now if theta hat is normally distributed, then we can get some things from the probability properties of the normal distribution, the following probabilities about the absolute error. So probability of theta hat minus theta more than equal to sigma, or one standard deviation sigma, which is the standard deviation or the standard error of the estimator really, is going to be 0.32, and it's to be more than 1.6 is going to be 0.10, more than 1.96 sigma, which is the 95%, which is 0.05, and more than 2.58 sigma theta hat, these are all sigma theta hat, is equal to 0.01. That means is if we did repeated sampling and computed theta hat every time, approximately 68% of the values of theta hat would lie within one standard error of theta hat. If we did repeated sampling, so we are doing repeated sampling and we are calculating theta hat every time, 68% of the values of theta hat would lie within one standard deviation. 90% of theta hat would lie within 1.64. 95% of the values of theta hat, which is the expected value of theta, estimated value of theta in repeated sampling, 95% will lie within 1.96 standard error of theta hat, and this is where the confidence interval comes into. But value of standard error or standard error of sigma theta is mostly not known and needs to be estimated from the sample data. So then we use this is the standard error of the estimator, but we don't know, so we need to estimate that, so we need to put a hat on top of that also. So that also follows a sampling distribution of this also. So because when we say the sampling error of the estimator, right, we to get the sampling error of estimator, we go all the way here, we need to calculate the variance. And how do we calculate the variance? The variance is most of the time we don't know, because variance requires all the sample TIs, all the different TIs. So this is the variance. Variance is estimated value of Ti minus expected value of T. Expected value of T will be needing to be calculated from here. So we don't know the population uh, uh, variance. So that needs to be estimated from the sample itself, because we are taking just one sample, and so that is why we get a sigma t. But the whole point of this thing here is that the absolute error calculation uses this formula, that this is the parameter and this is the value that you estimated. And if we did repeated sampling and we calculated the theta every time, 68% of the theta will fall within one standard error. This is the sampling distribution. Now we have a example. So we have a population of 6, n is equal to 6. Values of yi are 8, 3, 1, 11 and 4 and 7. We choose a sample of 2. Now we want to calculate the mean yi's and then verify that sample mean is unbiased estimator of population mean y. So the point is that if you have a n of 6 and you want to take a sample of 2, and 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 then you what population you can take, because the population is going to be 1 2 3 4 5 6. So how many can you take? Now you can take a total of and choose 2, which is going to be 15. So what you would do is that in 15 you will have to select the sample number, and then you would say 1 2 1 3, and then you do sample observations. And sample observations, if it's 1 and 2, then the yi's are going to be 8 and 3. Then you can do y hats, which would be 5.5, and you will calculate all the y hats. And you already know the population mean, because this is the population mean of all 6. So it will come out to be 5.667, and each of these will have a pi, which is 1 by 15. So expected value of y hat is just going to be pi times ti, which is going to also come out to be 5.667. So that is why we are saying that the sample mean is an unbiased estimator of the population mean.